In this video, I want to talk to you about assessing the normality of data. So the typical problem we've been looking at with normal distributions has been, here's a data set or here's a situation and it's normally distributed. Here's another situation and it's normally distributed. Well, how do we know? How do we know if a distribution is normal or not? And so when a data set comes our way, there are 4 different techniques I want you to be aware of for assessing the normality of the data. I want to go through each of the techniques with you, and then we'll do an example where I show you kind of how we would actually approach using these techniques. The first technique for assessing normality is descriptive plots. And this goes back to our descriptive statistics, the graphical descriptions of data. And there were 2 plots specifically, a stem and leaf plot and a histogram that allowed us to see the shape of quantitative data. And so one easy way of assessing normality is just to plot it, just to take a look. Does it have the nice symmetric mound-shaped look that we'd be expecting from a normal curve? So it's just a visual display, and it's a visual test as to whether you think it's normal or not. Very straightforward, very easy. The second technique, it's got a fancy name, it's called the empirical analysis, but really it's an easy idea. Think about earlier in the semester when I talked about the different rules for interpreting a standard deviation. The rule that we used depended upon the shape, right? If we had skewed data, for instance, we used the modified empirical rule. If we had mound-shaped symmetric, what we now call a normal distribution, we use the empirical rule. And so if the data is normal, doesn't it stand to reason that the percentage of the data in that distribution should follow the empirical rule numbers? And so what we'll do is we'll take the data set, we'll calculate a mean and a standard deviation, and then we'll create the 1, 2, and 3 standard deviation intervals around the mean, x bar plus or minus 1 standard deviation, plus or minus 2, plus or minus 3. And then we'll count. We'll count how many of the data values that we have in the data set fall within 1 standard deviation, within 2, within 3 standard deviations of the mean, and then compare those percentages. So we'll take the counts of the number of observations that fall in the intervals, express them as percentages of the total amount, and then check them against what we'd expect to see in a normal distribution. 68, 95, 100. Now I should mention to you that, let me get my pen here, and I don't think that's a pen, this is the pen, here we go. This is the number I want you to pay particular attention to. A lot of times what we get are skewed distributions. And so if you have a typical skewed right distribution, think about it. Which rule would be applicable here? Well, here we use the modified empirical rule. And if you remember the numbers, I'll give them to you again. The modified empirical rule said between 60 and 90% fall within 1 standard deviation. Between 90 and 100%, well, that's going to look a lot like that. And between or approximately 100% fall within 3 standard deviations. So when you're dealing with skewed data, the 95% and the 100% numbers still hold up pretty well. It's that first standard deviation number. It's at 68%. A lot of times what we see in skewed data is this number is quite a bit higher than 68%. And so that's the one I want you to pay particular attention to when you're conducting the empirical analysis. Look at the 1 standard deviation number. If you have some crazy distribution, it's not symmetric, not skewed, all the numbers are probably going to be off. But particularly the first standard deviation is the one you want to pay attention to. And so that's a number that we would take care and take a look at. So the empirical analysis is number 2. And I guess I should mention there's 4 different ways of assessing normality. There's not the right one and the wrong one. You would want to look at several of these and just kind of get a consensus. Take a look at the empirical analysis. If it looks pretty good, then the stem and leaf plot, the histogram, would probably support that. My least favorite, my personal least favorite, is this third one. Calculate what's called the IQR, the inner quartile range, divided by the standard deviation. Now, the inner quartile range is actually the difference between the lower and upper quartiles. That's where it gets its name. The lower and upper quartiles are the 75th and the 25th percentile. And so a lot of times on printouts, the printouts will give us the 75th, the 25th percentile. You can take the difference between and divide by the standard deviation. In normal curves, in normal distributions, this value should be pretty close to 1.3. Sometimes people use 1.34. I'll just make it an easy 1.3. So I'll say the closer this value is to 1.3, the more normal the data set. The reason this is my least favorite is because I think this one can be the most misleading. You can have non-normal data that just gets lucky and gives you a value close to 1.3. Typically, if you have a normal data set, it's probably going to be fairly close to 1.3, but Non-normal data sets can also give you that. So I would never use this one by itself. I would always use this one in conjunction with maybe one of the others. And then the last method of assessing normality is to create something called a normal probability plot. Now, back in the day, these things were a nightmare to actually draw. I remember using logarithmic graph paper, and I'm just getting upset thinking about it, so I'll just move on. Nowadays, of course, it's very simple to create any kind of plot, including this one. You just point and click. And so creating a normal probability plot, the straighter the plot, the more normal the data. Now, my caution for you here is even an extremely normal distribution isn't going to give you a perfect straight line. But if it's fairly straight, then we're going to say that the plot or the data is approximately normal. And so again, I would use this in conjunction with some of the others, get a consensus of, yeah, it looks like all the different techniques are saying looks pretty normal, and then go from there. So those are the 4 techniques. Now what I want to do is I'm going to go get a data set and I'll show you how we'd actually use these in practice, and then we'll wrap up this video. All right, so to illustrate how we assess normality, I'm going to use a data set that I collected from my spring Stat 1 classes. And you can see in this data set that I have a whole bunch of different variables. Some of them are qualitative, which don't make any sense to use when you're assessing normality, but some of them, like the age of students, the GPA of students, the exercise times, how many hours did my students exercise per week, and how much debt, student debt, do you think you're going to have when you graduate? And that would be in thousands of dollars. So the first student here would say 25,000. So we have 1, 2, 3, 4 quantitative variables. And what I want to do is try to come up with, get an assessment of which one would you say is most normal. Now there may not be any normal, but which ones would you say are most normal? And so what I'm going to do is I'm going to start with the chapter, or let's say I call them the descriptive plots. So let's start with a histogram. And so I can choose my, let's say the age of students. I'll put that in and let's take a look at that. And we're going to assess the shape. And you can see that most of the students' ages are right here. And then there's this long tail, very skewed, right? You wouldn't say this is normal at all. All right, so I'm going to come up here. And now let's say, what's the second one? Let's go with GPA, that's the second one. So I'll go there. And that's not normal either, but it's normaler. Is that a thing? I don't know if that's a thing, but it's more normal than the ages look like. It's skewed a little bit to the left here. Okay, so let's go and take a look at the exercise times. So I'll throw that in there. And you can see they're very skewed to the right as well, right? So again, not very normal. And then the student debt data, look at that, and that's very skewed to the right. So there's not a lot of normal here. But if I was assessing to see which is the most normal, I think based on at least the histograms, we would have to say it's the GPAs. All right, so now let's take a look at stem and leaf plots, and I think we're going to find the same thing. Now the nice thing with stem and leaf plots is I can put them all on one plot. So I'll put age, GPA, exercise, and debt, or I shouldn't say on one plot, but I can ask for them all at the same time. Now remember, when we're working with stem and leaf plots, we got to rotate this 90 degrees so that we can see the shape. And you see a skewed right shape here. You see a little bit skewed left. I think it actually looks a little bit more normal in this plot than it did in the histogram, but still I wouldn't call it a great normal distribution. And then exercise times here, extremely skewed, and the debts are extremely skewed. So again, the chapter, right, I keep going wanting to go and call it a chapter number in the textbook. The descriptive plots would indicate that the GPAs are probably our most normal of the 4. All right, the second analysis is usually the most difficult, at least time intensive. So in order to come up with the descriptive statistics that I need, I'm going to go and ask the age. I got them all right here. I asked for the quartiles. Yeah, that'll work. So let's see. So let me make this a little bit bigger so that we can see it perhaps a little bit better. There we go. And for each of my variables, I'm given some statistics, right? And the statistics that we're going to need are the first quartile, and that's the way statistics presents it, the first and the third quartile. That's the 75th and the 25th percentile. So I happen to have a little calculator right here. So when I take the ages, when I take the difference between the quartiles, 20 minus 19 is 1. That's pretty easy. And then divide by the standard deviation. I'm just doing the math on my calculator right now. I get 0.36. 0.36. In normal distributions, we'd expect that number to be close to 1.3. And of course, we know the ages aren't real normal, so that's very far away. So that would, the interquartile range divided by the standard deviation would say, nah, that's not normal at all. The GPAs, remember, we think the GPAs are the most normal. Let me take the third quartile to 3.7 and subtract a 2.99. That's 0.71, and then divide by the standard deviation of 0.5036, and I get 1.41. So it's not exactly 1.3, but boy, it's pretty close, right? It's not far away, a lot closer than the ages were. All right, so now let's take a look. We have two more skewed right distributions. So again, I'm going to work with the exercise times now. I'm going to take 10 minus 4, oh, that's 6. Then I'm going to divide by the standard deviation of 6.9792, and I get a 0.86, 0.859 and some change. So that's not very 1.3-ish. And then the last one here is going to give me something pretty similar, because look, 16 minus 0, that's 16. That's easy to do. And then divide by 16.985, and it gives me the 0.942. So again, the GPAs, excuse me, again, the GPAs appear to be the most normal, which isn't a surprise because we already looked at the plots. But that's how you'd use the interquartile. I shouldn't say that. That's how you use the interquartile range over the standard deviation. Okay, now that wasn't the one I initially started with. That's the third one. The empirical analysis, that's the one that's even more labor intensive, because in empirical analysis, what I need to do is I have to take the mean plus or minus one standard deviation. So 20 plus or minus 2 point, let's just make it 8. And then the mean plus or minus 2 standard deviations, and then the mean plus or minus 3 standard deviations. And I get 3 intervals. And then I go back to my data set and say, all right, what percent of the ages fell within that first interval? What percent fell within the second interval? What percent fell within the third interval? Labor intensive, right? Likewise, we could do the same thing for the exercises and for the GPAs and for the debt. So take 3.3121 plus or minus that, then plus or minus 2 times that, plus or minus 3 times that, and then go back and count how many of your observations fell in the interval, express it as percentages, and compare them. It's a lot of work. It's a lot of work. If I ask you to do that on a project, I'll give you some better instructions in this. But that's the empirical analysis. And so the last one's pretty easy. It's a normal probability plot. We find it here. The normality test, the normal probability plot. And so now you just ask for your specific variables. And display a reference line is checked. That's giving you this straight line, just in case you don't know what a straight line looks like. So we're looking for the dots, the data values, to be straight. Well, the ages are extremely curved. It's indicative of a skewed distribution. So let me change that. Let's take a look at the I'll do the GPAs last. And that's a little bit better, right? A little bit straighter, but still extremely curved. Let's take a look at the debts. The debts were very skewed as well. And so the best one we have, based upon our other techniques, would be the GPAs. Yeah, look at that. It's pretty straight in this region, and then comes off the line. So it's still got some funkiness, some curve attached to it. And the reality is we don't really have a whole lot of normal distributions to look at with this data set. So none of these techniques are going to end up with the conclusion that we have a normal data, but that's okay. I just want you to be able to assess the data. So that's how we would do it. Now in your projects, I'm going to ask you to work with one or more of these techniques and assess the normality of one of your variables, and we'll see what you come up with. So hopefully this helped you understand how those 4 techniques work. So long.